Good afternoon, everyone. I'm Ziyu Liao. I come from National Central University. I'm pleasure to be here for today's presentation. Today, I want to introduce the IoT-based optical detection platform for diagnosis of oral squamous cell carcinoma. Here is an outline of my presentation. First, I will introduce oral cancer and our motivation to do this project. Then I will talk about the materials and methods we use to achieve our goal. Third is the results. And last, I will make a conclusion. Oral cancer is like a sore in your mouth, and it doesn't go away. And it can be life-threatening if not detected and treated early. Unfortunately, about 50% of new cases are found in stage 3 or 4, and it led to a low survival rate. Every year, oral cancer occurs globally in about 600,000 people and result in 330,000 deaths. When we look back to Taiwan have 2.5 million high-risk groups because of the use of tobacco, betel nut, and alcohol, which are being seen as the main risk factors in oral cancer. And the incidence rate is like the slideshow, which is higher than other countries. There are many kinds of methods for detecting oral cancer, including physical examination, endoscopy, X-ray, and so on. But these methods are time-consuming and require expensive and bulky equipment, and the patient may feel uncomfortable during the diagnosis. Therefore, we want to invent a point-of-care and expensive device to do a quick and high-sensitive detection test instead of using conventional methods. The main idea to detect oral cancer quickly is to target the biomarker interleukin-A in saliva. Interleukin-A, so-called ILA. Previous studies have shown ILA was detected at higher concentrations in saliva of patients with oral cancer. Use light sensor to measure the concentration of ILA. The light through the saliva solution, and sensor will record how much light onto the detector. Using this information, we can get the concentration of ILA and to know if the user has the oral cancer or not. And here comes our detection system. It contains 3 parts: the device, microfluidic chip, and smartphone app. The device contains a programmable microcontroller unit, LEDs, a microfluidic chip, photon detectors, and power supply. We choose the Cortex-M4 as the MCU for its widely used integrated development environment and its multiple programmable input and output channels. A 16-bit digital to analog converter is used to deliver a modulating signal to LEDs through the LED driver. LEDs will light up the samples in microfluidic chip, and the photon detectors will collect the signal and transmit the data to the MCU. Finally, the data will be delivered to smartphone app through Bluetooth. This is the design of microfluidic PDMS chip. It consists of 3 injection chambers, mixing channel, control chamber, detection chamber, and waste chamber. The reagent will be injected into injection chamber and be premixing at the mixing channel. The detection chamber and control chamber is the place in which optical immunosensor measure, and the exact solution will flow into the waste chamber. About the detection procedure of microfluidic, first, we call the capture antibody in the detection chamber, and the control chamber was not. Second, interleukin-A protein and detection antibody was loaded in 2 of the injection chamber individually. In the detection chamber, they were captured by the capture antibody, and in the control chamber, they will just flow away. Last, we loaded TMB substrate into the last injection chamber, then we could see the color change of detection chamber by the reaction of detection antibody and TMB substrate. After TMB substrate was incubated in the detection chamber and control chamber for 2 minutes, we use optical immunosensor to analyze the result. Finally, the measurement is initiated by smartphone app and operated by MCU in the device. Light absorbance intensity signal are obtained by 2 sets of LEDs and photon detectors, and the signal are transferred to the smartphone app via Bluetooth. This is a standard conversion table for IOA that we have acquired. It provides us a reference to convert the light absorbance intensity to the concentration of the target molecule. Using the equation for limit of detection, 3 picogram per milliliter is the LOD of our device for IOA protein. Additionally, the correlation coefficient of measured value is more than 99%. The results show that this protocol system can successfully obtain IOA biomarker concentrations and has the potential to assist diagnosis of oral squamous cell carcinoma at an early stage. In summary, it is a sensitive, compact, and portable device to detect interleukin-A, which is associated with oral cancer. Recording data directly through Bluetooth also make it a device that can satisfy the high demand for point-of-care testing. The combination of the handheld detector and smartphone could not only provide a powerful and cost-effective way to perform mobile detections, but also offer a direct way to deliver the results in real time. The device demonstrates a good measurement accuracy and shorter detection time on IOA, providing a portable and affordable resource to patients. In the future, we plan to expand the variety of biomarkers to be detected, making good use of this device. Thank you for your attention.